Hi there, friends and neighbors. I'm going to show you a complete example of a results section for a repeated measures ANOVA. You use this if you measure the same group of individuals repeatedly, or more generally speaking, if you have a blocking variable, and you want to see if the means change over time, if they change across the multiple measures. Now this is getting into territory that's kind of advanced, and so I'm going to keep this results section kind of light. There's a lot more detail that we really should be including, particularly as regards the assumption checks, which I'm just kind of going to gloss over in a pretty simplistic way. These are the pieces that should go into every results section: descriptive stats, graph, and inferential stats. The inferentials you state HO, H1 alpha, assumption check, which we're going to keep light. You really do need a more advanced class to do this properly. Confidence interval, test statistic, degrees of freedom, p-value, decision about HO, and interpretation into plain English. Okay, so let's see if these means are different over time, where we've got multiple means. I've got a data set already loaded up, and it is test scores. And so what I'm just start off, just jump right in with HO. The means do not change over time. In other words, all the population means are equal. H1, the means do change over time. Alpha, I mean anything you want as long as it's 0.05. If you have a reason to change alpha, that's fine, but you will need to defend it. I'm just going to choose 0.05. Now, statistical analysis, continuous variables, repeated measures ANOVA. If I do reject HO, I need to be able to figure out why, and that's why I will choose home as my pairwise comparisons. And what it does is do t-tests, that is paired t-tests, on each possible pair of means. I'm going to just look at test 1, 2, 3, 4, 5, and 6 to see if the test scores are changing over time. Okay, and I'll make a line graph that will give me information about that as well. So I'm going to click OK. Here's a nice line graph. I'm actually going to copy that. If you've got Windows or Mac, you can just copy it, right-click and copy it. My situation is a little bit different. I'm using Linux, and so I'm going to do it a little bit differently. R behaves a little bit differently on my machine than on yours. Okay, so I'm going to paste this into my Word document. Paste it here. Anchor it as character. Make it smaller. Cut it and paste it where the graph would go. There's my graph. Put that away. Okay. Next, I'm going to go look at the rest of the output. Let's see, do we have just the descriptive statistics anywhere? No, unfortunately it didn't give me the descriptive statistics, so I'm going to produce those separately. I go statistical analysis, continuous variables, numerical summaries, and I'm choosing test 1 through test 6, and I just click OK. Copy that table, copy the whole thing. Now there are no missing data in this example. So these 67 observations are the same. Sample size for all of them. So paste. Just paste it, then select it, and change it to Courier New, or Courier, so that it's a monospace font. And here are the means and standard deviations and sample sizes, also the 5-number summary. So those are my descriptive stats. Here's my graph. Here I've stated HO and H1 and alpha. Now, assumption check is kind of complicated. We assume homogeneity of variance. We assume independence, which is achieved by simple random sample. We assume that the variable is normally distributed, or n is very large. Let's say at least 30 for each. I guess n of 30 wouldn't work here. Well, anyway, for each group. I think I'm going to leave it at that. Then what else do we have? homogeneity variance, independence, normality. Oh, there's and this is tricky. We've got something called homogeneity of covariance. That's a little beyond the scope of the class. I don't want to talk about it too much. You get a test of it automatically in the output. I'll show it to you. We're going to violate the assumption. We'll never pass it. And then we just go on, pretend it's okay. So I'm going to scroll up and look at our ANOVA results. Here they are. By the way, homogeneity of covariance, also called sphericity. And here's the test for sphericity. And if it's significant, if it's statistically significant, then we violate the assumption. And we almost always do. And sure enough, we do here with a p-value of 0.01. So there's adjustments that you can use. Greenhouse-Geiser and Hunfelt are two adjustments you can use to fix that problem. I'm going to keep it simple for now. This being a relatively introductory class. Right-click, copy the ANOVA summary table. Well, I'm just going to say we do not meet the assumptions. But we're going to continue because it's a fun project. I'm going to paste my ANOVA summary table, select the table, and make it look pretty by making it a Courier monospace font. Here are my degrees of freedom for time, 5 and 330, 2 degrees of freedom values. There's my F, and here's my very small p-value. So p-value is less than or equal to alpha, so we reject HO. Now let's interpret what that means. We're not done yet. So all this tells me is that there is a change over time in test scores. Well, there is, let's just say it this way, there is sufficient sample evidence to support the claim that there is a change in over time in test scores. Now, we need to find out which means are different from which other means. We find that out by looking at the Holm follow-up comparison procedure. It's right here. I'm going to copy it. Using Holm follow-up comparisons, we see these mean differences. And we just look at these p-values. And if the p-value is less than 0.05, we say that that is a significant difference. And if it's not, we say it's not. We make it Courier. Okay. So, looking at 1 to 2, there's no difference. But 1 to 3 is less than 0.05, as is 1 to 4, 1 to 5, and 1 to 6. So, test 1 is higher than every one except for test 2. When we look at our graph, let's look back at that graph. You can see what that looks like. Is these two are not significantly different, but this one is actually higher than any of the other ones after that. Next we see test 2, 3, and 4 are about the same level, but then 2 is higher than 5 or 6. So what we've got then is these 3 are sort of a plateau, but it's higher than these guys. Okay. And so on. It's kind of useful to think of meaningful ways to look at not all of these pairwise comparisons, because there's, with 6 of them, there's 6 times 5 over 2 equals 15 possible p-values. There's 15 p-values in here. And that's a lot. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So if we just look at adjacent tests, 1 to 2, no difference. 2 to 3, no difference. 3 to 4, no difference. Up 4 to 5, that is significant. And then 5 to 6. So what we really see is that there's a drop-off from 4 to 5. But these guys are pretty much the same. They're dropping off slowly, but the real drop occurs at test 5. And then test 6 is also low. So that's what I would say if I looked at this. And so let's put that into our conclusion. The scores drop off significantly from test 4 to test 4 to test 5. Then they stay low. And that's I don't like this courier. Oh, who cares? It doesn't matter. Anyway, that's a complete example of a results section for repeated measures ANOVA. All right.